The technique you're going to learn today is basically running the product rule backwards. So back, October or so, when we were learning how to do derivatives, we needed a special rule called the product rule in order to be able to take the derivative of something that was multiplied as a product. And as such, you need a special rule to be able to do the antiderivative of that. All right, so let's review the product rule. All right, so if we've got the quantity A times the quantity B, and we're running the product rule through that for derivatives. Our product rule ends up with B prime times A plus A prime times B. What we need to learn today is how to run the anti-product rule when you want to take an integral of something or an antiderivative. So the process of doing that, the anti-product rule, is something called integration by parts. And we need U substitution to be able to do it. So what's the difference between regular U substitution and U substitution using this new technique of integration by parts? So every time we learn something new, it's to help us do something we couldn't do before. So let's think about last week. You didn't know anything about U substitution when you started last week, Monday. When you have U substitution, when do you know that you've chosen your U well? From last week. Yeah, go ahead, Lucas. Yeah, like everything extraneous that you have in the problem reduces away. Okay, so in U substitution, all extraneous or extra, not needed, terms reduce away. And if they didn't reduce away, then what did that usually mean? You hadn't chosen your U very well. But again, all of the problems were designed so that the right U choice would work. So then, of course, that means, well, what if those problems aren't designed that way? What if there's a problem where I choose my U substitution, I've chosen every possible U substitution, and all the extraneous terms don't reduce away? I need another strategy, and that's where integration by parts comes in. And so we call it parts because there's two parts. There's a U part and there's another part, a secondary part. All right, so integration by parts. When all extraneous terms don't reduce away. So here are the two parts, parts being plural. You are going to make a U choice. All right, then everything you don't choose for your U, okay, so you have your U choice, and then you're going to have your DU term, just like we had before. Okay, so that's not new. Everything you didn't choose for your U choice is going to be what's called DV. And that will be everything else. Once you have everything else, and again, these problems are designed so that once you know your dv, you can come up with a plain v which is going to be the antiderivative of your dv term. That's why it's called parts. There are 4 parts to this problem. There's the u-choice part that you make. There's the du part that you figure out. There's the dv part that was everything else that was left in the original problem, and then the v part that you figure out. These are called the 4 parts that you need for integration by parts. It'll make sense when you see me do it, but let me give you the formula as well. So what happens is you start with a question, and you need to divide the question into what you're choosing for your u and what you're not choosing for your u, which is going to be everything else. And you're going to call that dv. So you're going to take part of your problem, that'll be my u. Anything else that's left would be everything else. Once you've made that choice, the process is going to be, then that will be equal to your u choice multiplied by your v choice, those 2 things put together, minus your v choice and what you determined your du to be. Again, like I said, it'll make a lot more sense when you see it worked out. This part that you get right there should work out perfectly. If it doesn't work perfectly, your u choice at the beginning was wrong, and then you got to go back and choose something different. So let's practice how this actually works in an actual question. All right, so to keep that order in mind right there, uv minus v and then u prime or du. All right, let's try this. What is my problem here? Here we go. Okay, let's take a look at the integral of x times the cosine of x dx. Okay, x times the cosine of x dx. For now, I'm going to make the u choice for you, and then I'll tell you some kind of tips on how to make a good u choice. So what I'm going to do is I'm going to separate, and I'm going to make this part of my problem, that's what I'm going to choose for u. Everything else that's left is what I'm going to choose for dv. And the way we're going to organize this to kind of help us keep everything straight is we're going to put u in that upper corner, and we're going to put everything we picked for dv in that corner. And we're going to find the opposite for both of them. For u, we're going to find the du, and for dv, we're going to find the v. So in one case, we'll be doing the derivative to find du, and in the other case, we'll be doing the antiderivative, right? So when we go this way, that'll be doing derivative. When we go this way, that will be doing antiderivative. It's just a nice way of organizing it. I'll show you, it'll become a little clearer to you. All right, so let's set this up. I chose this time, and I'm going to choose my u to be x. That means everything else gets chosen to be my dv. So if my u was chosen to be x, what's the derivative of that? Okay, but I need it in dx terms. It's dx. Okay, Okay, yes, I know the derivative. Remember like we were doing before, if I choose u to be x, then du dx is going to be 1, but when I separate them, du is equal to dx. I need the du part, which is equal to dx. I don't want 1. I want it separated, so I have my dx part. Okay, now for the rest of that, now I got to do the antiderivative. So what's the antiderivative of cos x dx? It should work out perfectly. Sine x plus c. Okay. Now, the original problem, which I split up this way, is now solved by the following combination, and I had you write it down. It's u and v, which u is x, and v is that, not the plus c right now. We're going to put the plus c someplace else. So the u and the v part combined, so x sine x minus and then what came next? You wrote it down. The v part combined with the du part. Okay, and hang on to the plus c. We're going to put it at the end. So those two together, sine x dx, and then my plus c at the end. And again, that sine x dx should work out perfectly. And so the answer, x sine x minus, okay, what's the antiderivative of sine x dx? Negative cosine x plus my constant. And so the ultimate answer is x sine x plus cos x plus c. So my original question is answered by this expression. How in the world would you check your work? Okay, so if that problem works out to be equal to x sine x plus cos x plus c, how do you check your work? Take the derivative of that, which is going to need what rule? It would need the product rule on x sine x plus cos x, and you're going to end up back to where you started again. So do you see the combination here? I mean, I did yellow first, and then the antiderivative of what I circled in green. And we're just going to keep practicing and keep practicing, keep practicing until you're comfortable with this. Okay, now I chose the u for you this time. Okay, there is a nice, helpful, nonsensical word, like the word itself doesn't make sense, but it helps you to choose. Okay, and so when you make your choice, you want to apply the Lippitt test. So the question is, how do I make a good u choice for integration by parts? All right, and it's L-I-P-E-T. It's like when you learned PEMDAS back in the day. Please excuse my dear Aunt Sally. Okay, so that you knew what order to do things in. L-I-P-E-T is the same thing, the Lippitt test, so that you know which order to choose things first. So your first choice, if you get to choose, would be an L for logarithm. If there is a logarithm, that's going to be what you choose for u. That would be the top choice, the best choice. I stands for inverse trig. If you don't have a logarithm, but you do have an inverse trig, you're going to choose that as your u, and then everything else will be dv. I didn't have either of those in my problem. I didn't have a logarithm, and I didn't have an inverse trig. P stands for polynomial. A polynomial of any kind. Polynomial could be linear, it could be parabola, it could be cubic, etc. Any of those, which I did have. X in my problem was a polynomial because x is linear, and so I made that choice. That was my u choice. If you don't have a polynomial, then e stands for exponential. And the very last thing that you would choose, and you're trying to avoid if you ever at all possible, is a trig function, which in my case I had cosine, so I for sure didn't choose it because that would be the last choice to make. So using that little acronym will help you choose well when it comes time to making your U choice. So let's practice a couple more. All right, let's try the integral of 2x and e to the negative x dx. 2x and e to the negative x dx. So I recognize that this is going to be a good time to do integration by parts because it's a product. All right, this is a multiplication problem, and so you go, oh, okay, I'm going to try. Maybe you forget and you try regular U substitution, and stuff doesn't cancel out, and so you're like, bad, go and try something else. So this is going to be a good time. Now, according to the Lippitt test, what would you identify as your U in this case? Okay, so L logarithms, I inverse trig, P, any polynomials? What's the polynomial? Not just x. 2x. All right, 2x is the polynomial. It's a linear piece. So e is an exponential, which comes after polynomials. Okay, we want polynomials first. So we are going to choose our u to be 2x, which means everything else is the dv part of my problem. So I'll have 2x, and then everything else will be e to the negative x dx. Okay, so now I apply my derivative or differential rules and I separate. What will the result of the differential on 2x be? 2dx. And then what will the antiderivative of e to the negative x dx be? Okay, it's e to the negative x, but I have to remember to divide by negative 1. Okay, which is, and I have to use the natural log of e also. So I can clean that up. The natural log of e is 1, and dividing by negative 1 is a little awkward, so it just might be a little bit nicer for me to write negative e to the negative x. If you want to put your plus c here, I'm not going to mark you off if you don't, as long as you remember to put it at the end of your problem. So I'm not going to be a huge, big stickler if you don't put plus c right there, as long as you remember. All right, so my problem, which started out as 2x e to the negative x dx, can be rewritten as the combination of u and v, which is negative 2x e to the negative x, minus the combination of v and du, so minus integral negative 2e to the negative x dx. So I have a negative on the outside, and I have a negative on the inside. So I'm going to go ahead and make those positive. And remember, what you get for that second integral should be set up perfectly for you to do an antiderivative on. Should be, quote unquote, should be. Which leads you to think of, oh, she's probably going to tell me what to do if it doesn't. All right, so then we're going to have negative 2x e to the negative x. Yeah, I'll add the plus c at the end, yep. And then I do my antiderivative one more time, which would be plus 2e to the negative x divided by negative 1 and divided by the natural log of e, which I can clean up. And I'd much rather write as minus 2e and then plus c on the end. So what's the only difference between those two terms? Yeah, one of them has an x and one of them doesn't. Otherwise, what do they have in common? I've got e to the negative 2x, or e to the negative, what else do they have in common besides e to the negative x? What else besides a 2? A negative. So you will often see if there's a common factor there to pull out all of the common terms and leave you to write it as x plus 1 and then put the c on the end. When we get to part where you got to set it equal to 0 and solve, it's a lot easier if you've written it in factored form. Okay, how are you doing so far? Okay? All right, let's try another one. All right, I'm going to do another polynomial exponential combination. How about x squared e to the half x dx? Okay, again, you jump. Oh, it's a product. Public service announcement. If any of your homework questions are not products, they don't have to be done this way. Okay, you can go back to regular U substitution. Okay. All right, so let's apply the Lippitt test. And what should we assign as our U choice? X squared. It's a polynomial, which means that everything else is my dv choice. So I've got x squared and then e to the half x dx. Okay, so now I work through, all right, what are my differentials on these? So what is the differential for 2x? 2x, excuse me, for x squared was 2x dx. If you don't remember how to do that, then, okay, it was du dx is 2x, and then we have to separate the dx from both sides, so that's where that comes from. Okay, and then we want the antiderivative of e to the half x, which is going to be, it's going to be e to the half x divided by half and divided by the natural log of e, which can be certainly cleaned up, and so that I write this as 2. And then there's a plus c. So my original problem, which was x squared e to the half x dx, is now becoming the combination of u and v, which will be 2x to the second e to the half x minus the combination. So I've got 2x dx multiplied by another 2 e to the half x. So overall, I'm going to have 4x e to the half x dx. Okay, which should be integrable, but it's not because it's still a product. Okay, so it's still a product, so we're going to have to do it again. Okay, so we have to repeat the process. All right, so it's like we start over, and we're going to repeat the process just on that part. So we'll do it again. Okay, so we'll choose u for this one. Okay, so set this up. 4x will be my choice, which means e to the half x dx is left. So my differential on 4x will be 4 dx. My antiderivative again is 2 e to the half x. So now I set up integration by parts for this one. So we'll combine the u and the v. That will give me 8x e to the half x minus the integral of the next combination, which is going to be 8e to the half x dx. And now we breathe a sigh of relief because that one is integrable as it is. So I will have 8x e to the half x minus the antiderivative of this, which would be 8 e to the half x divided by the half and the natural log of e. So I want to clean all that up. And it would just be better if I put a 16 out in front. Plus c, because I'm done. But what was in front of all of this? Okay, so we got to back up a little bit. What is all of this replacing? All of this is replacing this only. And what's still in front of that? Well, yeah, literally, like what is immediately right in front of it? A negative sign. And in front of that, so really what I've got, now that I'm back to the answer for the whole question, is that the whole question is going to be, all right, back to the beginning, x squared e to the half x dx is equal to the original 2x squared e to the half x that I had, minus now the quantity that I got from the second time I did it, which would be 8x e to the half x minus 16 e to the half x plus c. So that negative has to be distributed. So I'll have negative 8x e to the half x plus 16 e to the half x. And it's still, I know, Oliver, that'll bother you a little bit, but I'm distributing a negative and it's still plus c, because distributing a negative to a constant doesn't change the fact that it's a constant. Okay, now what do you notice that all of my terms still have in common with each other? A 2 and e to the half x. So we want to take that out, and that will leave me with x squared minus 4x plus 8, and then plus c. All right, you ready for your last one? Instead of, because a negative multiplied by a constant is still a constant. The constant itself might be negative. We can add anything we want. All right, last one. So, of course, I have one more wrinkle I have to show you in our final one today. Okay, the integral of, e to the 3x cos x dx. All right, what shall we choose for our u? Okay, LIP, I got through all of those. E was my first one. So we're going to choose the exponential, and then we'll have everything else. Oh, this is a good one. All right, so we've got e to the 3x chosen, and which means everything else is cos x dx. So then my derivative, my differential on e to the 3x is going to be 3e to the 3x dx. And my antiderivative of cosine will be what? It is sine x. Okay, we're going to match up this way and that way. All right, so the original problem, e to the 3x cos x dx, can be solved with the combination of e to the 3x sine x, okay, that's the yellow circle, minus 3 e to the 3x sine x dx. And we still have what? We still have a product. So we will need to do it again. Only twice, it's okay. All right, so I'm going to kind of slide my work over a little bit, and we're going to focus on, all right, I got to do it again. So, okay, lip it. My u choice is now 3 e to the 3x, and everything else is sine x dx. So I need the differential on that, which will be 9 e to the 3x dx. And I need the antiderivative of sine of x, which is negative cosine of x. And then we'll do our integration by parts on that. So the combination of uv and the combination of v du. So we will have negative 3 e to the 3x cos x minus the integral of negative 9 e to the 3x cos x dx. So even though I have a double negative, I can clean that up. But I still have what? Still have a product. Never fear. Okay, let's remember what's in front of this. So let's look back. What is in front of what we are working with? So we are just really just doing like a timeout for right here. So what's directly in front of it is still a minus sign and still the e to the 3x. So watch what happens. All right, so let's look at the whole thing. We have e to the 3x cos x dx was our original problem, equals the e to the 3x sine x minus, now the minus is going to affect what I've got going on here. So I'm just going to go ahead and take care of my distributing my minuses as I go. So my minus will affect the negative 3x. That will change me to a positive 3 e to the 3x cos x. My minus will affect my integral. So if you don't mind, I'm going to put the minus there, and I'm going to put the 9 in front because it's a constant, and we learned that we can pull constants out to the front. Cos x dx, and I'm going to put my plus c at the end. Okay, let's just take a good look at what we've got right now. Compare the integral we started with to the integral we now have. What do you notice? They're the same. I've got one of the integrals over here, and now I'm back because what do e to the x and sine x always just do? E to the x just keeps staying e to the x, and what does sine x and cos x do? They keep changing, so it only takes me 2 times to get back to cosine again. I'm going to add 9 e to the 3x cos x dx to this, which means I got to do it to the other side. I like terms. They're the same. So these cancel out. And how much am I left with on this left side? If I take one of the integrals and I add 9 more to them, what am I left with? 10 of e to the 3x cos x dx. And on the other side, they're all canceled out. So I've got e to the 3x sine x plus 3 e to the 3x cos x plus c. So all I got to do is get rid of that 10, and I will have an answer for my original question. So how do I get rid of the 10? I just divide. And so my original question, e to the 3x cos x dx, will be 1/10 of e to the 3x sine x and 3/10 of e to the 3x cos x. And I'm really sorry, Oliver, but it's going to be plus c again. I know we're dividing by 10, but it's still a constant divided by 10. And that is the answer. Okay, and what would blow your mind? How would you check that? Take the derivative, and you know what you're going to end up with? E to the 3x cos x when you take the derivative. Okay, so this is a very isolated case that only happens, okay, think about Lippitt. What 2 things were we working with there? the E and the T. And when you have an E-T combination, okay, it's going to be like that, but it only takes two. It only takes two cycles of integration by parts for you to end up with the same thing you started with. Okay, that's an isolated case. You don't have, it's not like I gave you 8 of those to do for homework or anything. All right, I gave you 1, maybe 2, okay, to do for homework. But the rest of them will only take a couple, take one iteration of integration by parts, or maybe